Next, we're going to talk about non-negative matrix factorization. The recent developments in technology have given us different kinds of data which are in huge dimensions. As a result, most of the classical analysis tools fails to analyze these data properly. Processing this massive amount of data requires powerful methods for their presentation and dimension reduction. In one case, we deal with non-negative data. Examples of non-negative data include pixel intensities composing an image, amplitude spectra, occurrence counts of a particular event, and so on. However, it is not advisable to use popular matrix factorization, such as SVD or factor analysis, on this data since they cannot guarantee to preserve this non-negativity constraint. This has made the development of non-negative matrix factorization very important. It is one of the most popular low-rank approximations used for compression, visualization, feature selection, and noise filtering. The idea is it replaces the original data with a lower dimensional representation. This is obtained by subspace approximation. We are going to talk about what this means immediately. It constructs a set of basis elements such that the linear space that they span approximates the data as closely as possible. Then we look at a linear combination of these basis elements to approximate the original matrix. Now these basis elements can be used for identification and classification, which makes NFF a very powerful unsupervised learning technique. This technique actually automatically clusters similar elements into groups and is a very valuable alternative to common clustering algorithms. It can also be regarded as a possible substitute of principal component analysis in the context of feature learning, of hidden Markov models, and many other areas. By providing a low-rank approximation, the non-negative decomposition maximizes hardware efficiency, since the low-rank matrix requires less storage than the original one. Also, it helps us provide a cleaner and more efficient representation of the relationship between the different data elements. There are several fields where NMF have been successfully applied for analysis of high-dimensional data. For example, image processing, bioinformatics, signal processing, and so on. Now let us talk about the method in a bit more detail. Non-negative matrix factorization decomposes the original data by searching for latent features that are presumed to be responsible for the generation of the observed variables. One suitable way to characterize the relationships between multiple variables is assuming that each element of the data matrix is a linear combination of a specific entity based on several factors. Specifically, a set of n-dimensional non-negative data vectors are placed in the columns of an n cross m matrix V, which is our original data matrix, or also called the target matrix. Here m is the number of entities. The target matrix is then approximately factorized into the product of two non-negative factor matrices. That is an n cross R matrix W and an R cross M matrix H, such that V is approximately equal to the product of W and H, with the constraint that W and H are both non-negative matrices. Here the original columns, that means the columns of V, represent the data points. The columns in W are the latent features, and the columns in H represents the coordinates of each data point in the factor matrix W. The rank R is usually chosen to be a small number, that means it has to be smaller than both n or m, such that it satisfies n plus m times r is less than the product of n and m. This assures that W and H are smaller than V, and their product can be regarded as a compressed form of the original data matrix. In this way, the information that is contained in V can be summarized and split into R factors. This parameter R plays a crucial role. Too high of a value for R could result in potentially serious overfitting problems, whereas too small could lead to a bad representation of the data. If R is actually equal to M, for example, then we can use the product of W and H to get back the original matrix V almost exactly, but at the cost of overfitting. Between the two matrices W and H, the matrix W is called the basis matrix, and the matrix H is called a mixture coefficients matrix, since its column vectors provide the weights that are used in the linear combination of the columns of the basis matrix. So if we look at this picture, think about one element of V. This element of V can be represented as a product of a certain row of the matrix W and a certain column of the H matrix. Here the W's represent the basis and the H represents the corresponding coefficients which determine the weights. The non-negativity constraints placed on the elements of the factor matrices are compatible with the intuitive notion of additively combining parts to generate the whole representation. This is how NMF learns a parts-based representation. Interestingly, the columns of the matrices W and H are often sparse, since they generally contain a large portion of the vanishing coefficients. Sparseness is one of the greatest strengths of NMF, since a sparse representation represents a majority of data using only a few active factors, making the feature set and coefficients easier to interpret. Let us talk a little bit about this matrix factorization. The factorization of the matrix V can be achieved through numerical algorithms that find at each iterations new updated values of W and H that minimizes a certain cost function. A majority of these algorithms uses a block coordinate descent scheme. Namely, they optimize a loss function with respect to alternatively one of the two matrices W or H while keeping the other fixed. The justification for using for such an approach is that this optimization problem, which is nonlinear, is not simultaneously convex in both W and H, but the subproblem in either the basis matrix or the coefficients matrix is actually convex. Moreover, this problem is also generally symmetric in W and H, and so most algorithms actually focus on updating only one among the two matrices, using the same update even for the other one. Every algorithm of this type is repeated until a convergence criterion is met, which is typically performing the numerical operations for a fixed number of iterations. Although the natural stopping criterion would be terminating the procedure when the approximation achieves a certain threshold, that means V minus the approximation W times H has a certain metric norm less than epsilon for some positive epsilon, the computational effort to check this requirement is huge. Therefore, most of the algorithms fix the number of iterations a priori. The general algorithm framework is as follows. We have a non-negative matrix V, which is our input, and then we have a factorization rank R, which we decide a priori. Then we have some initial matrices W0 and H0, which is our initial guesses, and then we keep updating W and H alternatively and then we output and rank our non-negative matrix factor of V. Now these different estimation procedures developed for NMF differ for two main aspects. That is the objective function that represents the quality of data representation, and secondly the actual numerical algorithm employed to optimize it. Let us first talk about the objective function. To find an approximate factorization WH for the original matrix V, we need to define a loss function that quantifies the quality of the approximation. This loss function L is a function of the original matrix V and the approximation W times H. Common cost functions are based on the squared Euclidean distance between the two non-negative matrices V and WH. Some other objective functions like the generalized Kullback-Leibler divergence is also used in practice. The nonlinear optimization problem then minimizes this objective function with respect to the matrix factors subject to the non-negative constraint. The next thing that we should talk about is initialization. All NMF algorithms need to be initialized with a value of W0 and H0. Now there is no global minimization algorithm, and so the choice of the initialization is extremely important. A good initialization can produce faster convergence to an improved local minimum while also increasing the speed and accuracy of the algorithms. To address this issue, several seeding methods can be used which need to be performed only once. For example, methods based on independent component analysis, where you basically perform an NMF, but we assume that the columns of W are independent. There are also other approaches like clustering techniques or non-negative double singular value decomposition. Another important thing that we need to talk about is the choice of R. If this value is too high, we know that there is a potential risk of overfitting, and if it's too small, then the approximation could be just poor. It is common to decide this value through trial and error unless you have some prior knowledge based on the specific domain theory. Several approaches have been proposed to further help users find the optimal value of such a parameter, such as applying SVD and looking at the decay of the singular value of the input data matrix, choosing the first value for which the residual sum of square curve presents an inflection point, and so on. Here is a little application to the iris data, and for that we need to install the BioBase package and also the NMF package that performs the non-negative matrix factorization. So we are trying to perform the NMF on all the columns except the species column, and we are going to use rank equal to 2. Now for the method there are several algorithms available. I have used the Lee method here, and you can look at the options of the algorithm by looking at NMF algorithm, open and close parenthesis. Now you can also choose a certain seed, and there are different ways of choosing a seed. I've used a random 1, 2, 3, 4 as my seed. The dot options equal to small letter p3 means that we are requesting 3 CPUs for parallel computation, but if the parallelization is not possible, then the small letter p allows us to perform sequential computation. You can also look at more details by looking at the NMF vignette. Once you have performed the NMF function on the iris data and you have saved it in a variable a, then you can look at fitted a to get the product W times H, which is nothing but the approximation of the original matrix of the iris data. Now remember that in the approximation there is a basis matrix and there is a coefficient matrix. The basis matrix has 2 columns and the coefficient matrix has 2 rows. You can look at this by the .coef and .basis functions. Now let us look at an interesting application to image analysis. So we have loaded the image and we have plotted the image here. As we can see, this image is in black and white and it's a brain image. Now we convert this image to a grayscale and we convert this image to a matrix. Then we find that the rank of this matrix is 233. We are going to use the method Lie, rank equal to 10, on this matrix to perform our non-negative matrix factorization. Remember that the fitted function gives us the approximate value, that is based on rank 10 instead of 233. And the as.cimg function converts it to an image. As you can see, this is the recovered image and it is quite blurred, but it still captures the overall structure of the original image. But since it's quite blurred, we realize that rank equal to 10 is a bit too low. So if we convert to rank equal to 50, which is still quite of a drop from 233, we see that the quality of the image has improved quite drastically. And we can see most of the important patterns that are to see in this image.